Hello friends, welcome to my channel. Today we're reading this book, Designing Machine Learning Systems and Iterative Process for Production-Ready Applications by Chip Yuan. This book summarizes many machine learning system-related topics really well and is very informative. I'm impressed by the wide coverage of this book. I also like Chip's writing style. She explains complex technical concepts really clearly. I enjoyed reading this book. It's actually really hard to summarize this book since there is so much information. So I'm going to try to summarize and highlight key points of the book that I think are important. Okay, let's get started. First, let's talk about how to handle data from the system perspective. There are two common data formats, row major format and column major format. CSV is row major, which means consecutive elements in a row are stored next to each other in memory. It allows faster data writers, and accessing rows will be faster than columns. Parquet is column major, which means consecutive elements in a column are stored next to each other. It's more compact, easier to use, and it's better when you have to do lots of column-based reads. Pandas is actually built around the columnar format. Data models describes how data is represented. There are two types of data models, relational models and NoSQL models, which includes the document model and the graph model. Data storage engines, also known as databases, are the implementation of how data is stored and retrieved on machines. This book mentioned two types of workloads that databases are optimized for. The online transactional processing, OLTP, which inserts transactions as they are generated. An example of a transaction can be tweeting or ordering a ride. The online analytical processing, OLAP, is designed to aggregate data in columns to answer analytical questions like what is the average price. Both OLTP and OLAP have become outdated. Today, we have transactional databases that can handle analytical queries. There are three modes of data flow. First is data passing through databases, which requires access to the databases. Read or write from databases can be slow and not ideal for applications with latency requirements. Second is data passing through services using requests, using REST and RPC APIs. Structuring different components of your applications as separate services provides you a microservice architecture. Third is data passing through a real-time transport like Apache Kafka and Amazon Kinesis. Because data passing through services can be complicated and synchronous, meaning that one service down can cause all the other downstream services to be down, we need a broker or a real-time transport to coordinate data passing among services. There are two types of real-time transport. In the PubSub model, any service can publish to different topics in a real-time transport, and any service that subscribes to a topic can read all the events in that topic. In a message queue model, an event is often has intended consumers, and the message queue is responsible for getting the message to the right consumers. Having data in real-time transports allows you to do computation on streaming data. You can do computation in parallel using streaming technologies like Apache Flink, which is highly scalable and fully distributed. The strength of streaming processing is in its stateful computation. It is possible to only do the computation with the new data and then join it with the older data computation. The second part of the data section talks about how to handle data from the data science perspective and how to create training data. There are several sampling methods for creating training data. First is non-probability sampling. One popular method of the non-probability sampling is the convenience sampling, where you select your data based on availability. Simple random sampling gives all samples in the population equal probabilities of being selected. However, samples in rare class will unlikely to be selected. Stratified sampling divides your population into groups and then sample from each group separately. However, it is not always possible to divide samples into groups, and it's challenging when one sample belongs to multiple groups. Weighted sampling gives each sample a weight, which determines the probability of being selected. Reservoir sampling is the most fun sampling strategy, I think. If you want to select 4 samples, you put the first 4 elements into the reservoir. For each incoming element, for example, the 5th element, we generate a random number I that is smaller or equal to 5. If this random number is less than or equal to 4, we replace the ith element in the reservoir with the 5th element. If the random number is greater than 4, we can toss out this element. The probability of being selected for the 5th element is 4/5. The probability of later points being selected goes down. However, because later points also have a lesser chance of being kicked out from the reservoir, the final probability for each element being selected is the same. Importance sampling is based on Martin-Collo methods and is one of the most important sampling methods. For example, if you have to sample x from a distribution px, you can sample x from qx instead and weight this sample by px over qx. In ML models, we often need labeled data, which can use hand labels or natural labels. Natural labels describe where the model's prediction can be automatically evaluated or partially evaluated by the system. For example, if you take the route Google Maps suggested, by the end of their trip, Google Maps knows how long the trip actually took. There are several techniques to handle the lack of labels. Weak supervision, which uses heuristics to label. This book calls the heuristics the labeling function. For example, if nurse's note mentions a serious condition like pneumonia, the patient's case should be given higher priority. Semi-supervision leverages structural assumptions to generate new labels based on a small set of initial labels. A classic semi-supervision method is self-training. You start by training a model on your existing set of labeled data and use this model to make predictions for unlabeled samples. You add the labels predicted to your training set and train a new model. Transfer learning refers to the family of methods where a model developed for a task is reused as the starting point for a model on a second task. Transfer learning is especially appealing for tasks that don't have lots of labeled data. Active learning is a method for improving the efficiency of data labels. So instead of randomly labeling data samples, you label the samples that are most helpful to your models according to some metrics or heuristics. For example, you can label the examples that your model is the least certain about, hoping that they will help your model learn the decision boundary better. We often need to deal with class imbalance in machine learning models. Class imbalance can make learning difficult for the following 3 reasons. There is insufficient signal for your model to learn and to detect minority class. Class imbalance makes it easier for your model to get stuck in a non-optimal solution. Class imbalance leads to asymmetric cost of error. The cost of a wrong prediction on a sample of the minority class might be much higher than a wrong prediction on a sample of the majority class. There are 3 ways to handle class imbalance. You can use the right evaluation metrics. We all know that the overall accuracy rate is not enough for tasks with class imbalance because they treat all the class equally. Instead, we should pay attention to F1 score, precision, and recall. Those are the metrics that measures your model's performance with respect to the positive class in binary classification problems because they rely on true positives. We can plot the true positive rate against the false positive rate for different thresholds. This plot is known as the ROC curve. We want the ROC curve to be closer to the perfect line and the area under the curve AUC to be large. We can also use a data level method like resampling. Oversample the minority class and undersample the majority class. A popular method for undersampling is Tomac links, which find pairs of samples from opposite classes that are close in proximity and removes the samples of the majority class in each pair. A popular method of oversampling low-dimensional data is SOMTE, S-O-M-T-E, which synthesizes novel samples of the minority class through sampling convex combinations of existing data points within the minority class. Then finally, we can use algorithm-level methods. Cost-sensitive learning manually defines the cost metrics with the weighted average for all possible classifications. Class balance loss weights the loss function by the number of samples in each class. Focal loss gives higher weight to samples with a lower probability of being right. I have only used focal loss. I think it might be the most popular one. Okay, so once we have the data ready, we can think about how to engineer features from training data. First, we need to think about how to handle missing values. There are 3 types of missing values. Missing not at random is where the reason a value is missing is because of the true value itself. For example, high-income respondents don't want to disclose their income, that's why it's missing. Missing at random, this is when the reason a value is missing is due to another observed variable. For example, female respondents don't like to disclose their age. Missing completely at random, this is when there is no pattern when the value is missing. People use deletion or imputation to deal with missing values. This book also talks in detail about the best practices of feature engineering. I'm just gonna list all of them here. You can read them more in detail in the book if you're interested. So here are the best practices. Split data by time into train valid test splits instead of doing it randomly. If you oversample your data, do it after splitting. Scale and normalize your data after splitting to avoid data leakage. Use statistics from only the train split instead of the entire data to scale your features and handle missing data. Understand how your data is generated, collected, and processed. Involve domain experts if possible. Keep track of your data's lineage. Understand feature importance to your model. Use features that generalizes well. Remove no longer useful features from your models. So after creating your training data and engineering features, we can finally develop, select, and evaluate some ML models. There are 6 tips for model selection. I really like the first one. Avoid the state-of-the-art trap. A state-of-the-art often means that it performs better than existing models on some static datasets. It doesn't mean that this model will be fast enough or cheap enough or perform better for you. Start with the simplest models. Avoid human bias in selecting models. Evaluate good performance now versus good performance later. So when you evaluate models, you might want to take into account their potential for improvements in the near future and how easy or difficult it is to achieve those improvements. Evaluate trade-offs, which includes false positive and false negative trade-offs, compute requirement and accuracy trade-off, interpretability and performance trade-off. And finally, understand your model's assumptions. One method that has consistently given a performance boost is to use an ensemble of different models instead of just one individual model to make predictions. There are 3 ways to create an ensemble: bagging, boosting, and stacking. Bagging is shortened from bootstrap aggregating. Given a dataset, instead of training one classifier on the entire dataset, use sample with replacement to create different datasets called bootstraps, and train a classification or regression model on each of those bootstraps. Then aggregate the results using majority voting for classification problems or taking the average of the predictions for regression problems. Boosting is a family of iterative ensemble algorithm that converts weak learners to strong ones. Each learner in this ensemble is trained on the same set of samples, but the samples are weighted based on how well the ensemble classifies them. Stacking means that you train base learners from the training data and then create a meta-learner that combines the output of the base learners to output final predictions. In your model development, you can perform distributed training using either data parallelism or model parallelism. Data parallelism is where you split your data on multiple machines, train a model on all of them, and then accumulate gradients. There is a consideration of synchronous SGD and asynchronous SGD discussed in the book. It was quite interesting to read. Model parallelism or pipeline parallelism is a technique to make different components of a model on different machines run in parallel. When evaluating a model, it is essential to know the baseline you are evaluating it against. You can use random baseline, simple heuristics, zero-rule baseline, human baseline, and existing solutions. There are some common methods to evaluate your model beyond overall accuracy metrics. Perturbation tests test how sensitive a model is to noise. Invariance tests make sure certain changes to the input should not lead to any changes in the output. Directional inspection test ensures that certain changes in the input should indeed cause predictable changes in outputs. I have made a video previously going through a paper in detail on those specific modeling behavior tests. I will link it in the description below. There are also other metrics like model calibration, confidence measures, and slide-based evaluation, which separate your model into subsets and look at your model's performance on each subset separately. One of the reasons slide-based evaluation is important is Simpson's paradox, which is a phenomenon in which a trend appears in the several groups of the data but disappears or reverses when the groups are combined. Next section is model development and prediction services. One fundamental decision that you have to make is whether to use online prediction or batch prediction. Online prediction is when predictions are generated and returned as soon as requests for those predictions arrive. Batch prediction is when predictions are generated periodically or whenever triggered. A problem with online prediction is that your model might take too long to generate predictions. Batch prediction is good for when you want to generate a lot of predictions and you don't need the results immediately. The problem with batch prediction is that it makes your model less responsive to users' change preferences. And also, with batch prediction, you need to know what requests to generate predictions for in advance. Having two different pipelines for batch prediction and online prediction separately to process your data is a common cause for bugs in ML production. Building infrastructure to unify stream online processing and batch processing has become a popular topic in recent years for the ML community. One approach to reduce the time a model takes to generate prediction is model compression. Low-rank factorization is to replace high-dimensional tensors with lower-dimensional tensors. For example, MobileNet decomposes the standard convolution of size k by k by c into a depth-wise convolution k by k by 1 and a point-wise convolution 1 by 1 by c. Knowledge distillation is a method in which a small model is trained to mimic a larger model or ensemble of models. Pruning, in the context of neural networks, has two meanings. One is to remove the entire nodes of a neural network, which means changing its architecture and reduce its numbers of parameters. The more common meaning is to find parameters least useful to prediction and set them to 0. Quantization is the most general and commonly used model compression method, which reduces the model size by using fewer bits to represent its parameters. For example, instead of using floats, you may have a model entirely in integers. Each integer takes only 8 bits to represent. Another thing to consider is whether to run your ML model on the cloud or on the edge. It is the easiest to use a managed cloud service to deploy your model. However, it is costly, and edge devices allow your applications to run where cloud computing cannot. You can also worry less about network latency. Edge computing makes it easier to comply with regulations as well. This book also talks about compiling and optimizing models for edge devices, using ML to optimize ML models using AutoTVM, and then talked a little bit about ML in browsers using WebAssembly, WASM. WASM is an open standard that allows you to run executable programs in the browser. The main drawback of WASM is that because WASM runs in the browser, it is slow. Actually, Anaconda has recently announced PyScript, which is built on WASM to allow users to create rich Python applications in the browser. I have written a blog post on PyScript and I'll link in the description below. Once the model is in production, you need to monitor the model and keep it in production. The causes of ML systems failures could be software system failures or ML-specific failures. Software system failures might include dependency failure, deployment failure, hardware failures, downtime, or crashing. ML-specific failures might include production data different from the training data, edge cases, and degenerate feedback loops. A degenerate feedback loop can happen when the predictions themselves influence the feedback, which in turn influences the next iteration of the model. Degenerate feedback loops are one reason why popular movies, songs, books keep getting more popular. You can add randomization, for example, using contextual bandit as an exploration strategy, or encode the position information using positional features to solve this issue. There are three main types of data distribution shifts. Covariate shift is when px changes but py given x remains the same. For example, you know that the risk of breast cancer is higher for women over age of 40, so you have a variable age as your input. You might have more women over age of 40 in your training data than your inference data. So the input distribution differ for your training and inference data. Label shift is when py changes but px given y remains the same. Concept drift is when py given x changes but px remain the same. For example, because of the COVID, the conditional distribution of the price of a house given its features has changed. To detect data distribution shifts, we can use statistical methods, for example, using a two-sample hypothesis test like a KS test. And there are many other tests out there. We can also use timescale windows for detecting shifts because there could be temporal shifts that happen over time. To detect temporal shifts, a common approach is to treat input data to ML applications as time series data and use time series decomposition techniques to observe the trend. There are three main approaches to address data distribution shifts. The first approach is to train model using massive datasets. The second approach is to adapt a trained model to a target distribution without requiring new labels. The third approach is the most common in the industry today, is to retrain your model using the labeled data from the target distribution. Addressing data distribution shifts doesn't have to start after the shifts have happened. It is possible to design your system to make it more robust to shifts. It could be a system using multiple features, and different features shift at different rates. You might also want to design your system to make it easier for it to adapt to shifts. There are four areas of ML-specific metrics you might want to monitor and observe in your system: raw input, features, predictions, and accuracy-related metrics. The author is really passionate about continual learning and testing production. How do we adapt our models to data distribution shifts? The answer is by continually updating our ML models. Continual learning is largely an infrastructure problem. Most companies do stateless retraining, which means the model is trained from scratch each time. Continual learning allows stateful training, which means that the model continues training on new data, which allows you to update your model with less data. Your infrastructure should be set up to allow both stateless retraining and stateful training. There are three continual learning challenges. The first challenge is the challenge to get fresh data. It can be slow to pull new training data from data warehouses. It's better to pull data directly from real-time transports like Kafka. The biggest challenge is the evaluation challenge. To make sure that the update you do in continual learning is good enough to be deployed, the more frequently you update your models, the more opportunities there are for updates to fail. Continual learning also makes your model vulnerable to adversarial attacks. It is crucial to test each of your model updates to ensure its performance and safety. The third challenge is algorithm challenge. It's much easier to adapt models like neural networks than metric-based and tree-based models to continual learning. For example, the collaborative filtering model needs to use the entire dataset to build the user item metrics. However, there have been algorithms to create tree-based models that can learn from incremental amount of data. The 4 stages of continual learning is Stage 1, manual stateless retraining; Stage 2, automated retraining; Stage 3, automated stateful training; Stage 4, continual training. There are several techniques to help you test and evaluate your model in production. Shadow deployment deploys the candidate model in parallel with the existing model, but only serves the existing model's prediction to the user. A/B testing is often used to determine which model is better according to some predefined metrics. Canary release is a technique to reduce the risk of reintroducing a new software version in production by slowly rolling out the change to a small subset of users before rolling it out to the entire infrastructure and making it available to everyone. Interleaving experiments exposes users to recommendations from both models and see which model's recommendation they will click on. Finally, a simple bandit algorithm like Thompson sampling have been shown to be a lot more data efficient than A/B testing. If you would like to learn more about Thompson sampling, please watch my previous video on that. I'll link it in the description below. The book also covers infrastructure and tooling for ML ops, which includes the storage and compute layer, deployment environment, resource management, workflow management tools such as Airflow, Argo, and Metaflow, and ML platform tooling for deployment, model store, and feature store. Okay, so that's a lot of information. I hope you find this video helpful. Thank you, and I'll see you next time. Bye!